Welcome back to the unit of non-spherical particles. In the next part, I would like to talk about the moment of inertia in greater detail. For that, let me briefly summarize what is the challenge. Obviously, orientation is important for non-spherical particles. We have seen that we can use quaternions for solving that issue. The next challenge is that we need to attack this balance equation of the angular momentum. The issue is that this equation is defined in an inertial or global reference system. So this IN refers to inertial. In an inertial reference system, the moment of inertia tensor, this quantity here, is time dependent because it depends on the orientation of the particles. So if we want to solve this equation, we can only solve for the time evolution of the total angular momentum, but not for this angular velocity omega in here. So the core mathematical problem is that we cannot pull out here this moment of inertia in the inertial global reference system from the differential. This does not allow for this straightforward integration of the equation to obtain this omega in here. Please note, very important, that for spherical particles this moment of inertia is a global constant, doesn't change with time, and hence we have dropped this in all our equations before for the spherical particles. We must now take care of this, of course, for non-spherical particles. Hence, we have to look into the difference between a global and a particle-fixed rotating reference frame. Here again, the global or inertial frame. Here we have our very simple or relatively simple angular momentum balance equation that looks like this. We transfer now this balance equation to the particle-fixed or rotating reference frame that is oriented such that it coincides with the axis E1 and E2 of the particle under consideration. In this particle-fixed coordinate system, this equation looks like this. So we have a different form, we have a different set of equations that we need to solve because these are all vectorial quantities. You will see that later. The transfer from this to this coordinate system is relatively simple with this rotation matrix A, as we have seen already, and also mapping back is not a big challenge because we just have to multiply with this inverse rotation matrix. What is now the idea and the algorithm behind the calculation of this angular velocity omega in this rotating reference frame? First, I mentioned this already, we must pick the particle-fixed or rotating reference system such that it coincides with the principal axis of the particle. Here we use these subscripts 1, 2, 3. The reason for such a choice of the particle-fixed reference system is that the moment of inertia in this reference system is constant and has a diagonal form. So we just need 3 values, I1, I2 and 3, to characterize the moment of inertia of the particle. If we now evaluate the equation of motion in this particle-fixed reference system, we arrive at the famous Euler equations for rigid body dynamics. So this is again the angular momentum balance equation in the particle-fixed reference system. And if we now use this special form, we arrive at the set of 3 equations that form these Euler equations that are so famous. You see, we can now easily solve for the angular velocities omega 1, omega 2 and omega 3 by integrating these 3 equations at a time. So we can now isolate these time derivatives of the angular velocities. You have seen it on the last slide. And after we have obtained these angular velocities, we can do 2 important things. First, of course, we would like to update the quaternions to update the orientation of the non-spherical particle. And second, we can use the inverse rotation matrix to obtain the angular velocities omega in in the global coordinate system. And this is what we could have not done before without this smart transformation. This is it already for this small part on the details of the moment of inertia. I hope you enjoyed it. See you next time.